In a previous video, we used iron filings to show the form of the magnetic field around a straight wire carrying a current. We'll see that you can use a right-hand rule where you put the thumb of your right hand in the direction of the current flowing through the wire, and your right fingers will curl around the wire in the direction of the magnetic field. We will now apply the Biot-Savart law to this straight conductor with a current I flowing through it to find the magnetic field intensities around the wire. We'll place our conductor along the z-axis with the current flowing in the z direction. Our current element IDL then will be IdZ in the z direction. The vector that points from our current element to where we want to find the magnetic field intensity, uppercase R, will then be Z in the minus Z direction plus rho in the rho direction. From this right triangle, the magnitude of R is the square root of rho squared plus Z squared. So our unit vector is just the vector R divided by the magnitude of R. Here's the Biot-Savart law. For dl, we substitute dz in the z direction. For our unit vector, we substitute this, and for r squared, we substitute rho squared plus z squared. We have to integrate over where the current is flowing, and it's flowing from z equals minus infinity to plus infinity. AZ cross A rho is A phi, and AZ cross AZ is 0. So here's the final form of the equation that we have to integrate. The rest is just integral calculus, so I'll let you go through those details. Let's just jump to the final result. We see that the magnetic field intensity is I over 2 pi rho, and it's in the phi direction, so it does form these circles around our current carrying wire, and the field is in the phi direction as given by our right-hand rule. And the magnitude of the magnetic field intensity falls off as 1 over the distance from the wire. And we see that with the iron filings, because if we get far enough away, the magnetic field intensity is not strong enough to orient those iron filings. Recall the electric field intensity due to an infinite line of charge of line charge density rho sub L along the z-axis. It was equal to rho sub L over 2 pi rho and in the rho direction. So we see the similarities of the electric field intensity due to an infinite line of charge and the magnetic field intensity due to an infinite line of current. They both fall off as 1 over rho. The magnetic field intensity depends on the current that's flowing. The electric field intensity depends on the line charge density. So we see similarities, but now the big difference, the magnetic field intensity is in the phi direction and the electric field intensity is in the rho direction. They're at right angles. And this we will see continuously, that the electric and magnetic fields will be at right angles for similar situations.